So hello and welcome back to this online machine learning course. In the last video, we dealt about normalization. So normalization was an algorithm or technique to actually get a perfect score without usage of powerful classifiers. Now in this video, we'll be dealing about another technique also known as regularization, which solves a problem known as overfitting. So before we discuss regularization, we'll be dealing about the problem of overfitting. So for the time being, let's see this graph, right? This is a graph. We had dealt about this graph or these data points earlier in linear regression. Now, I could easily draw a graph like this, like this, like this, like this. Now suppose this was my training data. Now this curve, this red curve over here, perfectly fits my training data, right? And let's take the green curve out here, and the green curve is a line, it is actually a line which is an approximation of this curve or these data points. Now which one is more accurate for a new data point? Because in machine learning, we would be having a training data point and we want our machine or our algorithm to predict for newer results. So as you can see out here, this newer data, since due to so many anomalies or perhaps due to so many functions, perhaps it forms so complex a function that it would in the near future would collapse this way. I'm sorry, let me change the color. Would collapse this way, or it would be a curve like this. Whereas my regression would be a straight line, single straight line. So as you can see out here, this curve is a total wastage. A total wastage to my prediction, right, for newer data points. And so we do not want something like this to happen. And so we employ something known as regularization. So overfitting refers to a model that models the training data too well, because it has seen the training data so well that it does not care for the newer data coming into it. As for example, look at this data set. Now just look at this green part. As you can see out here, it is accommodating or classifying the red and the blue parts perfectly, correctly. And look at the black one. It has got minor errors for these points. Some minor errors like this point. There are some points like this, right? And so there are some minor errors, and it is not fitting the training data as good as my green curve. But the point is that for newer points, as you can see out here, the green curve might exactly converge to something like this, and my black one would still continue to move on like this. And so this is for newer data points. For the points it hasn't seen, my black curve is better predicting for newer data points. And so this is how we do not want overfitting, and we want to prevent overfitting in our model or training data. So how do we remove it? So we use a technique known as regularization, and it is used to prevent the model from overfitting the training sample. And it is basically a parameter that can be used by minimizing the error function. So we'll be dealing about this second line in the forthcoming few minutes. So let's see how we can do it. So let's assume that these black points are my training points, and this blue curve is an overfit curve, and this line curve is a linear regression curve, right? Now, how can you get the regression curve from this curve, from this blue curve? If simply, now this blue curve would be some function of a x to the power n plus b x to the power n minus 1 plus c x to the power n minus 2 and so on, right? Suppose, and there would be perhaps some g x plus h, right? Now if I delete these terms and only keep these terms of this equation, will I not get a line out of that? I'm bound to get a line, right? So if I prevent my model from accommodating or restricting only the smaller values like gx plus h and prevent it from other higher order of x's, I can actually save my model from overfitting. And regularization has been derived from this intuition. And so, before we move on to regularization, there are two types of regularization. The first one is L1 regularization. The second one is L2 regularization. Of course, lasso and the ridge are their respective names or alternate names. And so we, in machine learning practices, we use the L2 one more often. I would be giving you the reason behind this, but L1 has got its own facilities, it has got its own merit, and we'll be discussing about this. So first we'll be dealing about L2 regularization. So L2 regularization. So as you can see out here, the ridge regression adds a penalty to the error function, right? And the penalty over here is the sum of the squared of the values of the weights. So this was my loss function or the mean squared error, which we saw earlier in an earlier slide. And as you can see out here that this is my predicted x, right? The y which we used to see, the theta naught to theta 4 are the weights, and x1 till x4 are my features, right? Now this was my loss function, the lxy. The new loss function, let's name it as old. The new loss function would be the old loss function plus this term. Now this term is the regularization term, and it is some lambda times the sum of the squared of the values of the weights. And let me tell you the intuition behind this analogy. So for instance, if I take my lambda to be a very large value, right? It's a very large value. Lambda tends to some order of 10 to the power 6. And my goal in machine learning is to minimize this loss function, right? So but my lambda is fixed. So since this one is fixed, I've got no option but to somehow reduce my thetas. And since we are reducing the theta, my weights are getting less independence to actually stray from the original path. Let me show you what I mean by here. So what was happening in this curve was that the black curve was the original curve and the green curve was actually straying from the original path of the black curve, right? So this was happening because initially we were putting a lot of independence to the weights of our model, but now we are somehow we are taking up that independence, we are restricting that weights to travel in a given specific path, and so it is predicting in this form. And that is why this intuition often works, because you are stopping your weights, you are not enabling it to take up large values, to take up significant values for overfitting. Now let's get to the L1 regularization. So the L1 regularization, also known as the Raso regression, is something like this. The only thing that we are changed from the L1 is that there was a squared over here, but now we have just a mod of that. It's just the power of 1. And the penalty is the sum of the absolute values of weights. Now it has got one feature of, or one speciality, is that it is used in feature selection. The reason is that for values or for not important features, like I can have x1 features, x1, x2 till xn as our features, right? So till xn, for features which are not important, my beta j would be turning to 0. Of course, I won't be going into detail about why it turns to 0, but you can keep in mind that for not important features, lasso regression turns the beta values into 0 for not important features, the corresponding beta values. And it is thus used in feature selection, as it can be used to select the important features and reject the non-important features. So why do we use so less of lasso regression? Because as I told you before, lasso regression uses a modulus operator, and modulus is non-differentiable. So while gradient descent, you need to actually put forth certain conditions. You need to look after certain conditions for it to actually converge, and so it is indeed a troublemaking task, and so it is not a very sought after approach, and we generally use theta squared. And but in case of L2 regularization, we actually get the theta values get very small, close to 0 for values which are not important, and so it often works the same. Generally it works the same, and so that is why we use L2 regularization more, and L1 is not much preferred. And so that was for today, and thank you for watching.